When you want to travel a long distance, let's say from one continent to another, you book a plane flight and wait to spend a few hours in the air. However, when it comes to space travel, you need to travel faster because all the points of interest are so far away. Space explorers have always been looking for a way to travel faster than light, which will allow them to reach deep space faster. Basically, all methods discovered have significant disadvantages, but scientists have found a new way. How does it work and what are the requirements? Join us while we bring you a new way to travel faster than light. Light is fascinating and very important because without it would be difficult to watch this video. Thanks to the sun and other artificial light sources that humans have found, we can walk without running against objects unexpectedly. However, you have probably heard of light travel and fast travel. But how fast is light? Curiously, the exact speed of light is known and is the basis for most other measures. The speed is 299,792,458 meters or 983,571.56 feet per second. This means that light will travel about 186,282 miles in just 1 second. Light is so fast that if you turn on a lamp in a dark room, light fills up almost instantly everywhere and you won't notice that light travels. Another unit of measurement involving light is the light year, which is the distance that light can travel in a year. This value is approximately 6 trillion miles or 10 trillion kilometers. It is a way that astronomers and physicists measure immense distances through our universe. As mentioned before, the universe is so vast that it can take many years for light to travel from one part to another. To illustrate, light travels from the moon to our eyes in about a second, which means that the moon is about a second away from light. However, light takes longer, requiring about 8 minutes to reach our eyes, which means that the sun is about 8 minutes away. The light of Alpha Centauri, the star system closest to ours, requires approximately 4.3 years to get here. So, Alpha Centauri is 4.3 light years away. Other stars and objects beyond our solar system are a few light years away from us. So, in this case, that's why everything astronomers see in the distant universe is literally history. When they study objects that are far away, they are seeing the light that shows the objects as they existed at the time that light left them. As for many fascinating things that you can do with light, scientists have tried to find a way to travel at the speed of light. This is interesting because humans have finally become an interplanetary species. For example, the billionaire CEO of SpaceX, William Musk, wants to form a population on Mars. But its explorers have to endure at least 5 months of travel through space before landing on the red planet. This can even reach almost a year, depending on how close the two planets are. And with that, all the dangers that it brings before landing on the red planet. However, with the speed of light travel, they can make a long trip in less than 4 minutes. Researchers have tried many different methods to be able to travel at a very high speed. Even as scientists trying to announce the new discovery that we are going to bring to you in this video, there was always a problem that all the other methods could not solve. Even reaching 1% of the speed of light, which is still very fast, because it can take you from Los Angeles to New York in just over a second, is very difficult. The problem in a single word is energy. Any moving object has energy due to its movement, and physicists call it kinetic energy. To go faster, you need to increase the kinetic energy. The problem is that it takes a lot of kinetic energy to increase the speed. To make something go twice as fast, you need 4 times more energy. To make something go 3 times faster requires 9 times the energy. And so on. To get a teenager weighing 110 pounds at 1% of the speed of light would cost 200 trillion joules. This is the amount of energy that 2 million people use in the United States in one day. For example, the N-Drive was played as a technology that would take the farthest parts of the universe very quickly. This invention, which was even patented, theoretically works by imprisoning microwaves in a molded chamber, where its highlight produces impulse. The chamber is closed, that is, from the outside, it will simply appear to move without any fuel inlet or any output. The N-Drive is based on Newton's second law, where the force is defined as the rate of change of impulse. Thus, an electromagnetic wave, or M, travels at the speed of light at a certain moment, which will transfer to a reflector, resulting in a tiny force. This tiny force, accumulated in large quantities, is what allows the n-drive, which sounds simple, but also essentially turns our understanding of physics in our heads. No energy enters or leaves, which makes us question how the waves are initialized, how they keep moving, and where does their momentum come from? And where does their momentum come from? You can't have a spontaneous momentum created without an inexplicable impulse, and that's why many scientists don't take n-drive seriously. If n-drive works, then it invalidates much of what physicists know about the universe. n-drive was even tested by physicists from the Dresden University of Technology, who showed that the promising results obtained by NASA and the Chinese, showing the boost, were all false positives explained by external forces. However, the warp thrower shows great promise, as presented by Dr. Eric Lentz, a physicist with more than 10 years of experience in practical applications. Lentz was not even the first to work to make the warp thrower a reality, not only in science fiction. The first was Miguel Alcubierre, a Mexican mathematician. In 1994, his proposal became the beginning of official literature about warp thrusters. Alcubierre and warp drive, as it became known, require an impressive amount of energy, along with the hot exotic matter as a co-ingredient. This highly radioactive material is only theoretical, and it is not something that researchers have really observed in nature, much less created. A handful of variations have been suggested since then, including an update from 2010 of the Alcubierre Drive Physics Project, made by the former NASA engineer Dr. Harold G. Sonny White. His update reduced the amount of energy needed to a less frightening number, although it was not practical because the solution still required exotic matter, although significantly less than the Alcubierre solution. Another group of Swiss researchers, known as Applied Physics APL, presented his own concept. Interestingly, his impulse did not need any exotic material to create his bubble of water. However, his model cannot go beyond the speed of light, which is the holy grail of space travel. To explain how his concept is different from those already proposed, Lentz first points to the physical structure of the classic Alcubierre drive, on which almost all other solutions are more or less based. He said that the Alcubierre solution provided an intuitive image that a double engine would do, that is, to contract space immediately in front of the central region that contains the ship or transport and expands the space immediately behind. This shows the warp thruster as a curved wave in which a ship will ride to its destination. Even though it is the cornerstone of the warp trip, Lentz claims that it is not even the essential feature. Instead, he says a solution proposed by physicist José Naterio in 2002 that showed that expansion and contraction were not necessary to transform the cargo forward. This work led to the rethinking of how a fold could be created using only traditional material and not exotic material. Naterio was able to prove that the expansion could be trivial or zero in all places and still perform the same task of transporting a ship. This is a significant advance because this means that the exotic matter that impends the space in front of the theoretical passenger and behind him in almost all theoretical solutions of hardwood is no longer necessary, and when building on the theory of the swimmer, Lentz created his own variation, which he believes to be even more viable because it is rooted in conventional physics. In addition to this material difference key, Lentz indicated that his solution differs from Alcubierre's and most others, geometrically due to how the energy is placed around the bubble of hard water. In the Alcubierre solution, the density of energy and the curves are separated to the maximum, with the energy being restricted to a small bowl between the regions of high contraction and expansion. The curves and sources in the Lentz proposal are, instead, highly correlated, with the regions of high energy density and high expansion and contraction overlapping almost exactly. It is these geometric distinctions between its concept and the traditional concepts that make the Lentz proposal a potentially more viable solution than those proposed before. Of course, Lentz's warp drive is even more completely theoretical. However, it takes some steps can be taken immediately to try to bring its version of reality closer, which, like all previous theories, includes the reduction of the amount of energy needed. Where does Lentz want to take his warp thruster from? He says that the next goal is to make a warp bubble capable of moving at 1% of the speed of light using a fission reactor from modern times. The physicist says he would consider patenting his warp thrower, but he made it clear that his work is just part of a larger workforce and rapid growth in this area, and that the recent increase in new warp thrower concepts since the proposal of Alcubierre in '94 gives those in his field the hope that a real and testable version may be closer than we think. Lens says it has been exciting to see the progress that has been made recently in the warp thrower field. He thinks that many advances are ready to be made and is anxious to see what the next years will bring. Let's hear what you think about the speed of fast travel in the comments section.